The most important sets which are considered in mathematics are sets of numbers or number sets. And let's start with such set as the set of natural numbers. This set contains the numbers 1, 2, that is 1 plus 1, 3, that is 2 plus 1, and so on. It should be worthwhile to say that the set of natural numbers has the following characteristic property. If A is a subset of the set of natural numbers, 1 is an element of A, and the fact that X is an element of A implies the fact that X plus 1 is an element of A as well. Then the set A is identical to N. A is the set of natural numbers. Indeed, according to the second hypothesis, 1 is an element of A. So 2 is an element of A as well. Because let's take a look at the third hypothesis. And we have 1, the fact that 1 is an element of A implies that 1 plus 1 or 2 is an element of A. So 3 is an element of A, 2, and so on. So any natural number n is an element of A because it can be obtained from 1 by adding 1 n times. Thus, the set of natural numbers is a subset of A. But by the first hypothesis, A is a subset of n, so we can conclude that A is n. A is the set of natural numbers. The well-known mathematical induction technique is based on the considerate principle. The next set is the set of integer numbers. The set of natural numbers can be extended to the set of integer numbers, by adding 0 and negative numbers. Now let's move on to the next set. The next set is the set of rational numbers. Any element of this set can be expressed as a fraction. The following fraction: m divided by n, where m is an element of capital Z, or m is an integer number, n is a natural number. The set of real numbers, capital R, can be defined as the union of two sets: the set of rational numbers and the set denoted by capital I. This set, capital I, is a set of irrational numbers that cannot be expressed as the fraction of the form m divided by n, where m is an integer number, n is a natural number. For example, let's consider the following number, the square root of 2, that is 1.4142, and so on. There is no repeating in decimal places in comparison with, for example, the number 1 divided by 3, that is equal to 0.333, and so on. And finally, I'd like to pay your attention on our new set, the set of complex numbers. This set is denoted by capital letter C. Let's make one more example. We have three sets: capital A, capital B, and capital C. Our set A includes all elements x such that x is a natural number between 1 and 5. And let's specify our set capital A using the first way. So A, we need to write the capital A, then put the equality sign, then write the opening curly bracket and then list our elements. X, our x is a natural number between 1 and 5. So our elements are 1, 2, 3, 4, and 5. Well, our set B includes all even natural numbers between 1 and 5. So B, we need to write this letter B, then put the equality sign, then write the opening curly bracket, and then list our elements. Well, so we need to take only even natural numbers. And our B includes two elements, 2 and 4. For our set C, that is a set of odd natural numbers between 1 and 5, we have 1, 3, and 5, of course. The problem is to find the result of the following operations: A union B, B union C, A union B union C, A intersection B, B intersection C, A intersection C, and the following relative complements. The complement of B and A, the complement of C and B, and the complement of A and C, or C minus A, B minus C, and A minus B. So let's start with the first operation, A union B. We need to take all elements that are in B or in A. Well, look at this. Our set B is a subset of the first set, capital A. And of course, this operation gives us 1, 2, 3, 4, and 5, all 3, 4, and 5, all our given set A. Well, now, let's talk about the result of this operation, B union C. Well, look at this. We said that B is a subset of A. But at the same time, C is a subset of A as well. And moreover, these two sets, B and C, have no common part. So B union C gives us the same result. The result is the set A. Well, B union C includes 5 elements, 1, 2, 3, 4, and 5, and this is our set A. Well, the next operation, A union B. Oh, I'm sorry, not A union B, of course, A union B union C. A union B union C. I am talking about this operation. Well, we showed that A union B is A. So here we have A union C, yeah? Because A union B is A. Well, and once again, C is a subset of A. So A union C is A. All our 5 elements, yeah? 1, 2, 3, 4, and 5. Well, now A intersection B. So the intersection operation, or A intersection B, yeah, is a set of elements that belong both to A and B. So here we need to consider the common part of these two sets, but B is a subset of A, so A intersection B is 2, 4, 2, 4, yeah, all our set B. The next question, yeah, B intersection C. We need to calculate B intersection C. We need to find the result of this operation. Well, we talked about earlier, B is a subset of A, C is a subset of A, but this set B and this set C have no common elements. And this result, this set B intersection C, is the empty set. One more operation, A intersection C, of course, gives us CO135. Now let's try to find the results of these operations. A, the relative complement of B in A, or A minus B, the relative complement of C in B, and the relative complement of A in C. Well, let's begin with the first operation. O A minus B. So we need to take our set A, these elements, and remove elements that belong to B. These elements are 2 and 4. So here we have 1, 3, and 5. And what is it? This is our set C. Well, the next complement, B minus C. Of course, this result is the empty set. And the final operation, C minus A. C minus A, of course, gives us the empty set as well. Now let's talk about some characteristics of number sets. Well, a set A that is a subset of the set of real numbers is said to be bounded from above if there exists a number capital M, a real number capital M, such that the inequality A is less than or equal to capital M holds for all A from our set capital A. We can represent definitions in the shorthand form using these special mathematical symbols called quantifiers. The existential quantifier is the backward letter E, capital E. The universal quantifier looks like the upside-down letter capital A. Well, this number, capital M, oh, I'm sorry, I see some typo. Here, of course, the number capital M, not capital B, but capital M. Okay, the number capital M is called an upper bound of our set A. A set A is said to be bounded from below if there exists a number m, lowercase m, small m, such that the inequality A is greater than or equal to m holds for all elements from our set capital A. And this number m is called a low bound of A. Please note that the upper bound and the low bound are not unique. Apparently, if capital M is an upper bound, then m plus 1, m plus 2, m plus 3, and so on are also upper bounds. And we can say the same for low bound. Well, we can formulate the following proposition. But before we do that, let's give the definition. A set A is said to be bounded, just bounded, if it is bounded from above, both from above and from below. And now, our proposition. A set A is bounded if and only if there exists a real number m such that the absolute value of A, where A is an element of our set A, is less than or equal to this number m for all elements from our set A. Well, the least upper bound of a set is called the supremum, and it is denoted as shown on the screen. The greatest lower bound of a set is called the infimum. Let's consider the set of natural numbers. This set is bounded from below, and the first element of this set, 1, can be considered as the greatest lower bound or infimum of our set capital N. It should be noticed that the infimum and the supremum always exist for this set, for this considered set of natural numbers. We have that the supremum is equal to infinity. And also we can consider one more set, for example, the set of integral numbers. And for this set, we will have that the infimum is negative infinity. The supremum is positive infinity. Well, any non-empty set bounded from above has the supremum. This is our first statement. And any non-empty set bounded from below has the infimum. Now let's try to prove these two statements. Well, let the set A be bounded from above, and B is a set of numbers that bound our set A. If X, I'm sorry, not X, but A. If A is an element of A and B is an element of B, then A is less than or equal to B. Then, according to the continuity property of real numbers, there exists a number beta such that A is less than or equal to beta, and beta is less than or equal to B. So the following double inequality holds for our A and B. Yeah. Well, now let's consider this part of this double inequality. A is less than or equal to beta. Well, this implies that beta is a number that bounds our set A. Well, beta bounds A. Now, let's consider this part of the written inequality. Well, this implies that beta is the lowest number that bounds our A. So beta is our desired supremum of the considered set A. And any non-empty set, our set A that is bounded from above, has the supremum. We show this fact. Now, let's consider the second statement of our theorem. Any non-empty set bounded from below has the infimum. So let A be bounded from below. From below. And the set B is a set of numbers that bound our set A, capital A. Then, if A is an element of the set A, B is an element of the set B, then A is greater than or equal to B. Now, let's use the same strategy. Yeah, let's use the same property, the continuity property of real numbers. Well, according to this property, there exists a number beta such that beta is greater than or equal to B and less than or equal to A. And now, as in the previous case, let's consider this part. Well, we see that beta is a number that bounds our set A. And moreover, if we take a look at this part, we can conclude that beta is the greatest value, is the greatest number among these elements in B. So beta is our desired infimum. Our infimum exists. Let's consider two sets, the closed interval AB. Here x is greater than or equal to A and less than or equal to B. A and B are included in our set. And one more set, the open interval AB. Here, x is greater than A and less than B. So we are dealing with two strict inequalities. And our endpoints are excluded. Well, now I want to find the supremum and the infimum of these two sets. Let's start with the closed interval. I think it's obvious that the supremum and the infimum of this set exist, and supremum of our closed interval is equal to B. And by analogy, the infimum is A. Well, what can we notice analyzing this result? We see that A is an element of our set and B is an element of our set. So the supremum and the infimum are in our set. Now, let's take a look at this set or second set, the open interval, AB, and try to find the same two characteristics. Well, and here, the supremum is B as well, and the infimum is A. But in this situation, B is not in our set, and A is not in our set. And we can conclude that the supremum and the infimum, all this exist, but they might not be in this set, as in this example. Well, now, let's consider one more set, for example, capital X. And let's specify this set, let's define this set by listing its elements. 1 over 2, 1 over 3, 1 over 4, and so on. 1 over n, and so on. Well, now, we need to prove that this set is bounded. Well, the nth element of this set can be expressed as 1 over n. Let's write out this expression 1 over n. N is a natural number, so for this expression, we can write that 1 over n is greater than 0 and less than or equal to 1 for all natural n. For all natural n. And we see that for all elements, the following inequality holds. Look at this, 1 over n is less than or equal to 1. So, our set X is bounded from above. And one more result, 1 over n is greater than 0 for all n. So my set is bounded from below. Look at this, X is bounded both from below and from above, so X is bounded. Bounded. Now, let's try to find the supremum and the infimum of this set. Well, I think you've guessed that the supremum is 1, the infimum is 0. Supremum is 1, the infimum is 0. Let's prove this fact. Let's prove that the supremum of our set X is 1. And to prove it, to prove this fact, I'll use the following property of the supremum. Well, for any given positive epsilon, there exists an element X in our set X such that this element is greater than supremum of X minus epsilon. And one more statement. For any given positive epsilon, there exists an element X in the set X such that X is less than the infimum of X plus epsilon. I suppose we need to give some geometrical interpretation here. For example, for the first statement. Well, let's consider some set of numbers that is bounded from above. I don't know, for example, let it be this set here, from negative infinity to a. Then, of course, here it's obvious that a is the supremum of our set, and moreover, in this situation, a is an element of our set. Now, let's take some small positive epsilon. And consider this value, the supremum minus epsilon. So we need to move back a little bit. So this is our supremum of x minus epsilon. And we see that if A is the supremum, if we move back a little bit, there exists some number, we can identify some number from our set X that is greater than this value. This is our X. And for this case, we have, for example, now suppose our set looks like this. Yeah, our set is bounded from below, and in this situation, A is our infimum. And as you see, for all elements, for all x, yeah, for all elements, x is greater than or equal to A. Now, let's mark this value. Infimum plus epsilon. Epsilon is positive. It is a positive number. So let's put some point over here. This is our infimum plus epsilon. And if A is our infimum, there is an element from our set, suppose this element, that is less than this new value, infimum plus epsilon. Well, now let's consider some positive small epsilon. And now we need to identify whether some number, some element x in our set capital X exists or not, such that our x is less than supremum minus epsilon. Well, so our x is 1 over n. And our supremum is 1. Yeah, we need to prove this statement that supremum is 1, so let's take 1 for this value. Yeah. Well, and now let's form this supremum minus epsilon. And in our situation, this supremum minus epsilon is 1 minus epsilon. 1 minus epsilon. And now we need to identify, we need to find some n such that 1 over n will be greater than 1 minus epsilon. Of course, we can take 1 for this element. 1, of course, is greater than 1 minus epsilon. So this element exists, and the supremum is equal to 1. Now, let's consider the second statement and take some positive epsilon again. Now, we need to find some element that is that will be less than 0 plus epsilon. So this time I want to prove that the infimum of x is equal to 0. Well, now let's try to find this element. Let's identify this number n. For this reason, I'll flip over the both sides of this inequality, and of course, in this situation, we need to change this sign. So we have n is greater than 1 over epsilon. And for example, if epsilon is equal to 0.1, we can take 11 for such a number, yeah? If epsilon is 0.01, we can take 101 for such n. Well, so we can find this number exists, and it implies that the infimum is equal to 0. It can be useful to recall notations of number intervals. The geometrical interpretation of a real number is a point on the oriented line called the real line. And for example, the inequality A is less than B can be interpreted as A lies on the left from B. The table you see on the screen contains the main types of intervals. The table includes 3 columns for sets notation, equivalent notation in terms of inequalities, and the geometrical interpretation. Thus, we can distinguish, for example, closed intervals, half-closed intervals, open intervals. For the closed interval, we have the non-strict inequality, x is greater than or equal to a and less than or equal to b, and of course, some interval on the real line. While for the half-closed interval, we should replace the left inequality with the similar strict inequality, x is greater than a, but not equal to a, of course, and draw a hole on the real line. So a is excluded. The interval of our interest for future investigations is an open interval with center at x and with delta. Such an interval is called the delta neighborhood of a point x. We can include or exclude the center. If we exclude this center, it will be excluded. The neighborhood is called a punctured neighborhood. In most cases, it is needed to introduce 2 elements, positive infinity and negative infinity, and consider the extended real line. We also use the following notations for sets that are bounded on only one side. For example, the open interval from a to positive infinity, so this set contains all x such that x is greater than a, and here we see that we use the second way of specification. Our rule looks like x is greater than a. The first 2 sets are bounded from below, while the last 2 are bounded from above. And for example, for the first set, let's consider the first set, we can say that the supremum is positive infinity, the infimum is a. It should be emphasized that positive infinity or negative infinity are not elements of the set of real numbers. So being less than infinity doesn't mean being less than an element called infinity. So that's all for now. Thank you for your attention.